Hello, my name is Miles Bankson. I have just completed my PhD research at the University of Colorado Boulder, working in the AVS laboratory with my colleague Kieran Wilson and our PhD advisor Hans-Peter Schaub. We have developed a new type of electron gun which emits electrons across a broad spectrum of energies, and this is useful for laboratory simulation of the on-orbit electron flux environment. Materials interact with the space environment in a number of different ways. Energetic electrons in space can degrade the optical, electrical, and mechanical properties of spacecraft materials. For example, on the left here, we see a pristine sample of kapton or polyimide, which is widely used on the exterior of spacecraft. And then if that sample is degraded with 90 keV electrons at a space representative dose, you can see there's a significant change in the optical properties of that material. Similarly, kapton that's exposed to energetic electrons will have an increase in conductivity, in this case over 2 orders of magnitude. This is known as radiation-induced conductivity. There's a lot of papers out there that you can read which will discuss these effects in more detail, but the point that I want to make here is that material properties are actually dynamic. So if we want to understand the performance and behavior of a spacecraft at the end of its lifetime, it's critically important that we understand those dynamic material properties, how the materials degrade over time, so we can model it and develop predictive capability. The problem is that it's very challenging to accurately recreate the electron flux environment in the laboratory. In space, electron fluxes are broad spectrum, but conventional laboratory electron sources only emit electrons monoenergetically. So we need to find a way to accurately recreate the dose depth curves that are experienced on orbit so that we can study the dynamic material properties. Many labs out there actually just use a monoenergetic beam and assume that the degradation is the same, which is not a great assumption. 2 other options exist. One is to use a series of diffusion foils. So for example, you have a sequence of metals which are deposited onto the substrate at different thicknesses and in different configurations. Then you use a monoenergetic beam, you direct that at this diffusion foil, and then you get a multi-energetic beam out because the electrons scatter off of the materials in this foil. One facility, to the best of our knowledge, the only facility that actually uses this technique is the Cyrene facility at Onara in France. And they use a sequence of foils with a 400 keV monoenergetic beam. That beam hits these foils and scatters off to create spectrum seen on this dashed line, which actually matches the geospectrum relatively well over some ranges. The problem is that this is not experimentally tractable. It requires this very expensive and complex 400 keV beam, as well as a sequence of foils. So this technique is not widely used. The other kind of best practice for recreating the on-orbit dose depth curves is to use a sequence of monoenergetic beams. So for example, at the Aerospace Corporation, Martin Ciafalo's group, in this case, using a sequence of 11 different monoenergetic beams, one at a time, to recreate the dose depth curve that would be observed on orbit. Now, the problem here is you might want to simulate, say, 5 years in space over maybe a 2-week laboratory tests. These tests can take a long time. So if you have to do that 11 different times to accurately recreate the curve, as you can imagine, that adds a tremendous amount of cost and complexity to the experimental study. So, as we mentioned before, there's a strong need to understand the dynamic material properties. And in order to do that, there's a clear need for a straightforward and experimentally tractable broad spectrum electron source. So this is what we have developed. Our source consists of a series of aluminum stages. So we have square aluminum stages with a circle cut out in each one. And then we stack these stages up with thin insulators in between so that they're electrically isolated. Then we set up resistors in between each stage to create a voltage divider circuit so that the forwardmost stage is at ground, and then the rearward-most stage is at a maximum negative voltage. Then we use an ultraviolet light and we shine that down the inside of the tube, and that stimulates photoemission from each of these stages. So photoelectrons are emitted from the surface, and then because of the circular shape of each stage, they're accelerated towards the center, and then that voltage gradient sets up an electric field, which then accelerates those electrons towards the front of the device. Because the front stage is at ground, the ultimate energy of each electron is equal to the potential of the stage on which it was generated. You can see some pictures of our current prototype right here. This version has 54 discrete stages and thus can output simultaneously 54 different energies in a single beam. So we've developed this prototype and tested it in our vacuum chamber in the AVS laboratory, which you can see on the left. Here is inside the chamber, we have our broad spectrum source. On the left of this picture is our ultraviolet light, which shines on the inside of that tube to stimulate photo emission. And then we use a custom built retarding potential analyzer to characterize the energy distribution of that beam. And we've been successful in generating broad spectrum electron fluxes using this source. The solid lines here are results from the broad spectrum source. And by adjusting the maximum voltage applied to the rearmost stage, we can tune what is the maximum energy output by the device. So here's several spectra for 2, 3, 5, and 8 keV. So we have broad spectrum fluxes from the source, and then comparing that to the dashed line, which is fluxes that would be seen in geosynchronous orbit as measured by the Los Alamos MPA instruments. As you can see, the broad spectrum fluxes currently are several orders of magnitude above what would be seen in space. That's not necessarily a bad thing because, as I mentioned, you want to do accelerated laboratory tests. You don't want to simulate 5 years on orbit with a 5-year experiment. You want to be able to do that in, say, 2 weeks. There might be other instances where you do want to exactly recreate the on-orbit environment, and we'll talk momentarily about how that can be achieved. We've done some preliminary characterization of the beam. So we mounted the retarding potential analyzer on this linear translation stage and swept it underneath the aperture of the broad spectrum source, which you can see at the top of each of these pictures. At each position, we collected a differential flux spectrum. You can see here one example where the maximum energy was at 1,000 volts, so 1,000 EV. And then you can see here the position versus energy beam map. So there's a few features to notice. There's a hot spot here between 800 and 900 EV. That's actually occurring because we're only using one light source, and that light source is shining at an angle so that it hits the side of the tube. Most of that light is actually hitting the rearmost stages, and less light is falling on the middle and forwardmost stages, which is why we see this enhancement between 800 and 900 EV. Also notice that this spectrum is more of a crescent. It's not symmetric about the 0 position directly underneath the broad spectrum gun aperture. And again, the reason for that is that that light is only shining on one side of the tube rather than evenly illuminating the inside of the tube, which would then create a nice even beam map centered around 0. So to solve those two limitations of the current prototype, for a future design, the plan is to use multiple UV light sources. And by doing that, that will give us control over the shape of the spectrum. So we can adjust the intensity of each of these lights, and that will affect how many electrons are generated at each energy level. And by doing that, we can have full tunability over that output spectrum. Additionally, we can tune the entire thing up or down so that we could, as appropriate, output fluxes necessary for accelerated testing or direct recreation of the geo environment. So we've been successful in building a prototype device. Currently, we're outputting 54 energies in a single electron beam, with maximum energies achieved up to 9 keV. Work is in progress to extend that to higher energies, such as 30 keV, and then eventually all the way up to 100 keV. We do have a provisional patent in effect, and a full patent is pending. I focused here mainly on the material degradation problem, but this broad spectrum source would also be highly useful for validation of secondary electron measurements across the full range of energies, and also system level checks for plasma instruments. Thank you very much for your attention, and I look forward to discussing this with you further.